right? It's saying if the series B sub n converges and A sub n is between B sub n and 0, then A sub n must also converge. All right? I'll give a kind of a simplistic view of that. It's very much based on the squeeze theorem or the sandwich theorem. But if you have some function that we're modeling as, and again, I'm drawing it as a continuous function, even though it's not. I'll call this B sub n. Bless you. All right, so we have 0 here, we have B sub n, and as you go to the right, in both cases, you notice that the two curves, the two relations, I guess, are getting closer and closer. All right, specifically because the x-axis isn't going anywhere, while the curve associated with B sub n is getting closer and closer to the x-axis. So, it's reasonable to say that there is a convergence related to B sub n. Maybe it's not 0 and it just looks like it is, but there's definitely some kind of convergence going on. It could be 0.5, could be 3, I don't know what the scale is. But what this theorem is stating is that you could also have some A sub n that exists in between the two. So if B sub n is converging upon a particular number, and let's say it is converging with 0, eventually they're going to come to meet each other. All right, they'll come in contact. If you can get out to infinity, then they would come in physical contact with one another. Now, I'm telling you that A sub n is always in between 0 and B sub n. Eventually, wouldn't A sub n have to take on the same value? If it's being squeezed in between the two, whatever the value is of B sub n at that later moment in time, A sub n should also have that same numerical value. All right. In number 2, let's go in the other way. It's telling us that if A sub n is divergent, and we know that A sub n is between B sub n and 0, if A sub n is divergent, then B sub n also has to be divergent. All right, and a graphical representation of that would be some kind of infinite function. I'll just plot it here as like an exponential kind of jammy. That's my A sub n. Now, the only way I could draw B sub n, because again, A sub n has to be in between 0 and B sub n. So the B sub n has to either be above A sub n, or it could be the same as A sub n, but it can't be below. All right, so you start thinking about different ways in which you could draw a B sub n. I could draw it up here if I want, but as I get closer and closer to the right, well, I can't go past it. It would have to take on the same shape. So while A sub n is turning uphill, B sub n would also have to turn uphill. So A sub n is divergent because it's going out to infinity. B sub n would necessarily have to go out in the same direction. Right? Another possibility would be, yeah, maybe you started here and it merged with A sub n. That could happen. Right? Maybe you started up here, came down, touched it once, then came away, then came back in later on. But still, at the very end, you would have to turn upward because you can't, you're restricted. You can't go past B sub n. Right? So no matter how you draw it on the left-hand side, as you go to the right, it has to take on the same shape as A sub n, or at a minimum, go out to infinity. All right. So if we know that A sub n is divergent, then we'll know whether or not B sub n is divergent. So we need a couple of things here when they ask us to determine whether it converges or diverges. Well, we need another function because they're giving us something, we need to come up with the something else, all right? So they're giving us the a sub n. I need b sub n. All right? So the b sub n would be the parent function of the n behavior model. All right, so the n behavior model for rational functions, you get that by taking the term with the highest power on top and dividing it by the term with the highest power on the bottom. And then simplify. Okay? So we would then need to find the parent function of that. Fortunately, that already is a parent function. There's no other coefficient. So there's no multiplier of the n cubed, and there's no addition or subtraction going on. There's no transformation of this. Right? So we would call my b sub n the sum going from n equals 1 to infinity of 1 over n cubed. That is the parent. Right? So that's the first thing that we have to do, identify the parent EBM. Then we have to figure out the relationship between a sub n and b sub n. Because it's going to fall into one of these two categories. Both of them will be non-negative, but one is going to be bigger than the other. All right? So you could do that just by listing out the first term of the sequence related to this series. Plug in a 1. If I plug in a 1 here, I get a 1. If I plug in a 1 here, I get a 1 half. Right? So at least for the first term, it looks like the a sub 1, a sub n sequence would be smaller than the b sub n. But you could try it for a few more. All right? You pop in a 5. You don't pop in anything. Figure, okay, I don't know what this is, but this has a denominator that's 1 bigger. If I'm dividing by a larger denominator, I have a smaller fraction. You can look at it that way too. All right. So now that we have that relationship, I have to address convergence. 1 over n cubed plus 1, I couldn't handle that. That's why we're looking at a comparison test. Because by writing it as the n behavior model, I can now determine convergence here. Right? Because this is a p series. And this converges by the p-series test, specifically because the p-value is greater than 1. So, if b sub n is bigger than a sub n, and b sub n converges, this is that first diagram. A sub n would necessarily have to converge. All right? So, therefore, the sum from 1 to infinity of 1 over n cubed plus 1 converges by the direct comparison test. Just nothing too fancy here. The DCT. All right. So it's by the p-series test that we're able to determine that this one converges, but it's by using the direct comparison test that I can determine that this must also converge if this one converges. All right. So definitely some kooky stuff. The idea that we're using different tests within the same problem, that's pretty fun. Right? So, challenge again is once you identify your a sub n, we want to find the corresponding b sub n, and then the relationship between the two. All right. Parent function comes from, again, dividing the term with the highest power top and bottom. So 1 over 3 to the nth. Again, chuck a little summation in there with n equals 1 to infinity. that that's a poor quality equal sign. I'm just gonna make it look a little nicer. All right. So again, you can do it. You can do it a couple of ways: numerically, reasoning. You can even look at the calculator. You know, put the two functions in using x's and see which one is physically above the other. All right. So you know, I can do that. I mean, numerically, it's not bad because you plug in a 1, you get 1/5 versus 1/3, and you can just compare the two. But if you're more of a visual person, then maybe you want to do it this way. So 1 divided by 3 to the x power, and then 1 divided by 3 to the x. You could use a fraction tool, but order of operations is, I think, all right in this case. I do need parentheses to do it this way. Okay. So you can go to the window, play around with those settings. Oh, I have different colors. You can go to the table, look at the numerical values, or you could just I had it on dot mode from last class. All right, well, it looks nice. What do you do? So 1/3 to the x is my blue, and the red is the 1/3 to the x plus 2. All right, so it looks like blue is bigger than red. Okay, that's pretty consistent. So you can do it that way. I mean, it's really up to you. All right. So then, now what? You look at this and say, well, that's not a p-series. I only know how to do p-series because that's the thing you just taught, and it's fresh. Okay, but we don't just have p-series. We also have things like geometric series. All right, you could rewrite this as 1/3 to the nth power. All right, and I don't think, generally anyway, it doesn't really end up being this issue that confuses people. It's identifying it as a geometric series to begin with, where people have trouble. Where you're like, okay, yeah, it's cool, you did some algebra there, that's wonderful. How the hell did you know it's geometric series to begin with? Because once I know it's geometric, then I know to do all the stuff that you did after that. All right, so here's the key indicator. Variable exponent. This is not a p-series. So this is a geometric series. That's because we have a variable power. All right. So if a function follows the model of an exponential function, variable exponent, that's how you know it's geometric. All right. So if it's a power function, then you're looking at something that's p-series. All right. So something with a variable base but a numerical exponent. But again, that falls into two categories. The case where the power function is on the top of the fraction versus the bottom of the fraction. Right? But anyway, if you happen to know that this is a geometric series and you also happen to know how to get it in the proper format, then you would know that this converges by the geometric series test. And that's because the R value is less than 1. Okay? If your R value is less than 1, absolute R or otherwise, then you know it's going to converge. Okay, we talked about that last class. If it's anything more than 1 or more, then it's not going to. I mean, if it's 1, then it's constant. So the sum of a constant, you would just be adding the constant to itself over and over again. Like the sum of the number 1, for example. That sounds like it would be really easy to figure out, but that actually diverges because you're saying for each step in the series, you're adding another 1. So it would be 1 plus 1 plus 1 plus 1 until time ends. So the case of a constant is actually pretty complicated. But in terms of actually doing something with it, it's not that bad because once I realize that it is constant, then I would know it diverges. But it's not a geometric series if that's the case. All right. Now, we know, because it's the same relationship as above, the a sub n function is between the b sub n and the 0. So this one, the original, going from 1 to infinity of 1 over 3 to the n plus 2, would again converge by the direct comparison test, the DCT. Therefore. All right. So again, in C we have an a sub n. The b sub n comes from the parent function of that, of the n behavior model of that. So 1 over the square root of n, or 1 over n to the 1/2, that's a little bit nicer, a nicer way of writing it. That would be our b sub n. Right? So now what we need is the relationship between the two things.
Is it from 4 or 1?
Sorry?
Is it n equals 4 or 1? 4, right?
Oh, it's a 4. Correct.
Oh.
Thank you. It's not going to end up mattering as it turns out, but still good to have correct information written. So in terms of the 1 over n to the 1/2, we can figure out convergence and divergence pretty easily, because that's a p-series, and then we'll deal with that in a second. But the issue is it may not matter, because if the a sub n b sub n relationship doesn't hold up the right way, then it may be inconclusive. All right. So if you want to put it in your calculator, or if you want to reason it out, you should, in theory, come up with the idea that a sub n is bigger than b sub n. All right. So b sub n goes here, a sub n goes here. All right. And that's because in a sub n you're dividing by something smaller than you are in b sub n, so you'll end up with a larger decimal fraction, whatever. All right. So this diverges by the p-series test, specifically again because the p-value is between 0 and 1. All right. So this is the second case up above, this guy here. If the lower bound is divergent, then whatever's captured within it is also going to diverge. So this would diverge by the direct comparison test also. Well, all of it's by a direct comparison test, but this time it's divergent. So if that relationship didn't hold up, if you had a sub n being between b sub n and 0, and then you got divergence of b sub n, that would be inconclusive, because that would tell us that the upper bound diverged, but that wouldn't tell us anything about what was happening with the inner function. All right, so that's the case of this first graph here, where if b sub n diverged, so let's say that went up to infinity, it wouldn't tell us necessarily that A sub n diverged. It could diverge, it could converge. It would be completely inconclusive. So if that size relationship isn't in the proper order, then these conclusions cannot be drawn. All right.